So module 5 is an interesting module because it looks at, it's much more numerical in terms of doing approximations to solutions and looking at error. So the first thing we're going to do is approximate the value of a definite integral by using the midpoint and trapezoidal rule. I'll explain those to you. Determine the absolute and relative error in your numerical integration technique or your approximation. Estimate the absolute and relative error using the error-bound formula. Recognize when the midpoint and trapezoidal rules over or underestimate the true value of an integral. And then, of course, to learn to use Simpson's rule, which will give us better accuracy. Okay, so one of the things that if we recall, we know how to integrate many things, but how do we compute these integrals? Something like the e to the x squared dx. We know how to integrate e to the x. If this had an x next to it, we could use u substitution, but we don't have that. If this were an x squared, we could use tan inverse, but we don't have that either. And if this were maybe just log of x to the first power, we could do it, but what do you do with log of x squared? So these are some difficult integrals. And we can, if we have a definite integral, which is the integral from a to b, so now we're on a finite interval of a function, it is basically just the area under the curve of the function. And so we're going to use the fact that it's just the area under the curve of a function in order to be able to move forward. Okay, so the first method we're going to learn is the midpoint rule. Okay, and I am going to do the midpoint rule starting with n equals 1, and then we'll move forward with other values. Okay, so let's say we have, I really don't want that red, I really want that gray. Let's say we have a function, and the function is on the interval AB. And what I'm going to do is I'm going to find the midpoint. So the midpoint is going to be C, and C is equal to B minus A over 2. So that's the midpoint. I'm going to go up to the height of the midpoint. And when I go up to the height of the midpoint, that value is F of C. And then what I'm going to do is I'm going to draw a line exactly at that height. As such, and I'm going to find the area under the curve, under that line. And as you can see, it is a gross overestimate of the area, okay, because the area underneath the curve is nowhere near this big. So this is a gross overestimate. And if by chance it had been at the smaller value, it could be a gross underestimate. It just depends on where your function, how your function is. Okay, so this is the function. So therefore the area now, so the actual area. So let's see, I want to grab just a few pieces of information here. Okay. So I have one interval, so n is 1. Delta x is the space between them. It is b minus a, because it's just, that's the distance. My c, as I said, is supposed to be, oh, what did I write for c? C is wrong. C is wrong. That's why I'm glad I have it on here, because that's wrong. C is a plus b divided by 2. Okay, so now if I take my area and I approximate it, this length, this is the length b minus a, so that's this distance, b minus a, which I'm calling delta x. And then the height of the function is f of c, which is a plus b over 2. I get a. So therefore, I'm going to say that the integral from a to b of this function f of x dx is being approximated by the midpoint rule, where n is equal to 1, which is to just take delta x, which is b minus a, times f of a plus b over 2. And we will continue with this tomorrow, where we will actually find the formula for the midpoint rule, and then we'll move into the trapezoidal rule as well.